somewhere at the top. We're gonna put 5 problems on the front of the paper so you can space it accordingly, okay? So 5 problems will go on the front. All right, we put number 1. And we write the word formula. Number 1, formula. You can go any direction you choose. We'll put 5 problems on the front. These pictures don't need to be all that big. Like I said, this is just all problem 1 right here. Did you draw a triangle? It's tough, super tough. Okay, next to your triangle, would you put an S? My S is going to stand for, any guesses?
System.
Ooh, sides. How many sides does a triangle have?
3.
3, okay, so far so good. We're going to do a little picture of a triangle.
System.
How many triangles does a triangle make?
3. 1.
1. Okay,
3 sides.
part 1. All right, still question number 1. Would you draw a quadrilateral? Any quadrilateral. How many sides should you be drawing?
4.
4, okay. I'd like you to break up that quadrilateral into triangles. How many triangles go into a quadrilateral?
2. 3.
How many make?
2.
2. Okay, so you should have an S. So how many sides does that quadrilateral have? 4. How many triangles did it make? 2. Okay. Next one. Would you draw a pentagon?
Hold up.
A pentagon. How many sides should you be drawing? 5. So some 5-sided shape. It needs to have 5 sides. Then you need to break that pentagon up into triangles. Couple of things when you guys are drawing your pentagons. We can't have any intersecting lines. 2, 3. Some of you are drawing stuff like this. They can't be intersecting. I can go that. Something. You can't have intersecting lines. So how many sides on your pentagon? 5. How many triangles can you make in that pentagon? 3. Do one more shape. Would you draw a hexagon? How many sides is a hexagon?
6.
Very good. 6. Some 6-sided figure.
What? Yeah, I know. That's my problem too.
I'm sensing a pattern here. Of course, I'll do
So you know that your sides are 6. Now break that up into
4.
triangles.
4. You break the edges off and then you split between the middle and
That's
the
again.
to get
What points are those?
oh.
Let's go back and put some degrees. Inside a triangle, it will always be how many degrees? 180. So by your triangle, put 180 degrees.
On every
How many triangles is
How many
this?
triangles it makes?
How many should the hexagon make? It's 6 sides, so how many? It makes
4.
4 triangles.
Next to the 3 foot look
Yeah,
at
square.
that side. Next to 1.
Let's go to your quadrilateral. It made 2 triangles. So how many
360.
degrees are inside any quadrilateral?
360.
Okay, how'd you get 360?
I took 180 times 2.
Okay. Looking at your pentagon. There are how many triangles inside that pentagon?
3.
30.
3. So each okay, so how'd you get that, Haley?
I added 180 to 360.
Okay, what'd you get?
720, right?
Seems a little too much.
Oh, wait, I know.
5, 8, 60.
540.
540, good, so 540 degrees with
I don't
that.
know either.
All right, your hexagon.
There we
How'd you
go.
get a inch?
180 to 1.
Excellent, all right. Now, you're starting to figure out the pattern. Don't say this next one out loud, you should just see it on your paper. You can use your calculator to figure it out. I don't want to necessarily have to draw out a polygon every time and break it up into triangles to figure out what the degrees would be. So what would a 15-sided polygon, don't say this out loud, it can be on your calculator, on your piece of paper. How many degrees on the inside of a 15-sided polygon?
I'm gonna draw.
When you have it, you can show myself or Mr. Ward. I'm trying to eliminate having to draw it all out. No. Try again.
What's 13
Yeah.
2, 3, 4,
15-sided, what would it be?
Close.
Got it?
That's probably-
Nice.
Close.
Ah.
Really close.
Check with your group.
I just took 15 minus 2.
You know what you did wrong, Haley? Okay, when it was a four-sided, how'd you get 360?
How do you get that
How many triangles would in
number?
that?
Each one, only one, but then the sides are, so the triangles are.
All right, someone help us out. What is a 15-sided polygon? What'd you do to figure this out? You could, I mean, some of you could draw a 15-sided figure from all your triangles, but the step, Luke, would be what?
Alright, so 15 minus 2,
Why 15 minus 2?
because there's 4 triangles in a septagon, right? So
Hexagon.
hexagon. And there's 6 sides.
Look at
So
your
if there's a
pattern.
15-agon, there'd be 13 triangles inside it.
Very good. Nice. But it's-
Hard.
if you look at your pattern, it's always 2 less than whatever your sides are. So I was gonna make 2 less for the triangle. So you took 15 minus 2 to get 13, and then took that number times
180.
180, and your answer would be
2,340
2,340.
degrees.
Okay. Last step for part 1. What would a formula be? Let's say for any side I give you, if I gave you a 15-sided polygon, a 20-sided polygon, an 8-sided, an octagon, on your paper, write down what would the formula be? So I can give you any sided, any number. What would the formula be, or what would the steps I would need to take on my calculator? You're super close on the end.
Wait.
Anyone think they have it? Melissa, what do you got?
180 and parentheses S minus 2.
Okay,
Yes.
doesn't matter what variable they use, Mr. Ward?
Nope,
It's
not at all.
first side.
Yep, so S for side, some of you I saw used N, that works too. But you need to take whatever that number is minus 2, and that needs to be in parentheses. And then you're gonna multiply that answer by 180. Nicely done. Good work. All right, would you open up your books? That was part 1. Here's your second problem. Second problems are on page 422. You can keep your paper out. Okay. Review from last week. On page 422, you have problems 5 and 6. They can go on the same side of this paper. should be equal. To quadrilateral. Yep.
Good. Now, the last step, do the second check. Go back over. Let's see, start with offer. Do you want to double check your answer? Somebody try to ask. See if you're right. Maybe you're confused. Good, and now, throw in the answer. Go back. Put a measure control. And then move that place. Put it back.
So do it. There's more than 4 x's there.
Why?
I see x, 4x, 2x, x.
Then I think you should really result
Right, so all of this on the inside equals 360, right? So how many x's do you have on the inside? Right.
I didn't know it was 360. Because she said that squares 360, squares to Germany. I don't use all up to make that. Oh,
Oh, yeah. Interior angle. Yep, nice. All right, here's the thing. Did you miss the question? Does it go back and find what's in each one then? Now that you know your x?
I subtracted them each other?
What's that? You just add it. You just add it all.
That one's 46 and so is that twice. Oh, they got it on that one.
And if you want to check your answer, if you're kind of confused, let me know. Yeah. At least you read the instructions. Some people haven't been reading the instructions yet.
Oh, okay. 360.
One, and you would say four. Explain what we're doing. Okay, I agree, okay, so here's my question. These are just parallels. So, what I would do, have all four, how much all four have? That's how we go. Oh, hey, if those are parallel, you did it right. So. There you go, huh?
Last one is number 11.
Wait, I gotta put.
What do we do?
It's number 11, the last
Okay,
one.
good, I agree with that.
Is yours looking right? Okay. The last one is number
This
11.
number is what I'm worried about, that. Minus 10. Where's your picture?
It's not equal.
Yeah.
Yeah, okay.
That's the only difference. Only
Number
now.
11, the last one. We're not rocking this, we're working about 2 more minutes, see if we can get these problems wrapped up.
Question. You're correct in the first one.
Look, I don't remember, I'll for sure that I look back in, go back in your notes.
All right,
Yeah. Oh, we moved down to 11. We moved down to 11. So sorry.
It's right, okay.
I was looking at system.
Okay, so your error on this one is there's more than 6 X's. You did, yeah, 4 X and 2 X, we forgot about.
Oh.
I don't know how to do that.
Okay, okay. Mr. Worthing, I agree, answer the question.
Oh, what's up?
Okay, so in my notes I have
Number 11.
the formula, all I have is that.
That's bad.
Okay, so it equals this.
Yeah. Smarties already loaded up with sugar today.
Excellent, thanks, nicely done, Abby.
Yeah,
Do I have the time now?
Each one?
Or do I just have the time?
Find another X. Find another X.
Forgot about.
Leisure.
Right, so you need to use those all again on the inside. That's the last part of your equation.
I think it's 352 though.
Subtracted 8 from
He's already
36.
subtraction.
Hmm?
He's already subtraction.
Oh, you have.
Yeah. Be careful on those things, you know, and check that one out. He did the same.
Yeah.
There you go. All right, last one's number 11.
That's done. It's just done.
Okay. Go through board sixes right now, you can answer the question. What would be the angle, what would be the angle of each?
Dragon fishing,
What one's that?
6,
60. 62.62, is that what it says?
yeah.
No. That's not right. Probably have what's more than one.
Okay. All right. I know this is going to be a short time on that. What I'd like to do is have your notes out. To take those out in front of you right now. Some of you already have them out. You want to save this little piece of paper for right now. Maybe just put it off the side. Don't lose it. We'll maybe use it as a bookmark at some point. We're going to come back to it. This is something we're not going to get rid of today. We're going to actually come back to it at the very end. I want to do maybe a 5-minute little note section to talk about what our next couple properties are, to review some that we've previously done. And then we're gonna try to show how they apply and do some problems with it. So again, keep that half sheet of paper that you're just working on. Again, we're gonna be using our textbook on the next few as well. So just hold on to those. But those should have been the 3 problems you should have been working on. I'm gonna move the camera here and then we'll get started here. What was that? You just close it for right now. You don't need to put it away all the way. All right, here's the idea. Goal state. We've already accomplished one of them, right? Was to make sure we did that activity with Miss Edwards. To kind of review some of the properties we've done a long time ago, to talk about where they came from again, just to refresh your memory on how to do interior, exterior angles. We didn't do number of diagonals. That's something we'll do later, at a later time. What I want to do today is intro rectangles one more time. Go through the definition of what a rectangle is. We talked about this about a week or so ago. We talked about what the definitions of the different types of quads are, the 4 set of figures. I want to review the rectangle itself, and then we're going to get to 2 properties about them, which are theorem 613 and 614. They go insanely fast. They're really quick properties, very, very short, but I want to talk about them. Because we've been talking about just properties about parallelograms in general. I want to talk about properties that only apply to rectangles, if you have that specific shape, because that's what most people think of a 4 set of figures. Now, just remember, before we get too far in depth, and I don't want to make sure that we cut off the bell today, remember we have homework due tomorrow. That was the assignment that I gave, I think it was last Thursday, I think, when I was here. This is the assignment that's on the board. This is due tomorrow, page 407. It's based on parallelograms, knowing certain properties about them, and then you can solve. Okay. Now let's do the quick introduction. Definition of a rectangle. One more time. It is a quad with opposite sides parallel, right? Because that's a parallelogram. But then the other part of the definition, it has 4 right angles. So here's your picture. Now, this picture has some extra parts on it, right? So it's a quad with sides being parallel, but it has 4 right angles. Now, what you're looking at here is that there's some extra markers on this picture. Namely, certain walls are the same in terms of length. When you're drawing this picture, you don't need to put those markers there. The reason why is that that's just one of the properties we're going to eventually talk about. But the definition of a rectangle means that certain walls are parallel. I'll put double arrows here. There we go. They have certain walls are parallel, and then they have right angles in the corners. That's the generic definition of a rectangle. We talked about it. It's a type of parallelogram, right? Because the walls are parallel. The goal was to go through the basic properties, to review some that we've previously done, and hopefully this makes sense to you. Okay. Anyone need more time for that basic definition? So it's quad, opposite sides parallel, 4 right angles. That's what a rectangle is. Okay, let's get to the properties here. Real quick before I always forget this part. Notation. When they write in the book, they'll usually write the word rectangle, and then they'll put 4 letters down in a circular pattern. You don't need to. What I always say, because that's how they always write in the book, what I always tell people is that since it's still a parallelogram, it's still, it's a generic parallelogram, says opposite walls parallel, you are allowed to draw a box like that looks like a rectangle. If you want to put little markers in the corners, you can to show that it is a rectangle in the first place, has right angles. Then put the letters down in the corner, or beside it. They just have to go in a circular pattern, counterclockwise or clockwise, it doesn't matter. You can start with any letters you want, but as you spin around, just make sure you're connecting letter to letter. B to C, C to D, D to A back to B to back. I'll accept either one. The book uses this one, but I want to remind people that you're allowed to still draw the picture because it is still a parallelogram. All right, questions before we get to the basic properties today. And I'm going to go through this pretty quick. Things that we've already discussed. I'm going to get rid of all these markers. All right, the properties about rectangles that you should know as of this moment. Number one. On a rectangle itself, you should know that all four angles are right. We should know that that's part of the definition. So that should be like first and foremost, that's the first thing you should be thinking of. Okay, we even had a previous theorem that talked about right angles. What was that, 6-6 we did last week? Where if you had one right angle, all the rest of them are rights, but that's the definition of a rectangle. Okay? Now the properties that still apply to rectangles, even though we haven't even got very far into the chapter yet, basic properties you should know. The opposite sides are parallel and equal. That's why I have these markers on this picture. The walls are still equal because that was the first theorem we had. That was the first theorem we did last week. We had theorem 6.3. Right? The walls are equal on a parallelogram. That still applies. That doesn't go away. So if you have a rectangle, you can still move the walls across the picture. So somebody make up a random number.
12.
12. So if the top is 12, the bottom would be 12. Make up a new number. 8. If that right side AD here is 8, you can transfer the 8 over to BC. So these two walls are 8s and the top and bottom are 12s. You can do that. That is still what that property was from last week. We talked about that the opposite angles in the corners are equal. Well, duh, they're right angles. Right, that was theorem 6.4 or 6.6, if you will. Okay, that you can transfer that 90 degree to that other corner, and then A to C. We used that a lot last week. We talked about the consecutive angles were supplementary. In fact, Mitch, you even tried to use that today in some of our pictures. Okay, but the problem was trying to use that property on the pictures that we did today. They weren't parallelograms. When you look back at those shapes we did on the little slip of paper today. The consecutive angles didn't necessarily have to be supplementary on those pictures because they weren't parallelograms. This is. So the certain angles have to add up to be 180, no matter which direction you go. That was 6.5. Then one of the last things we talked about is the diagonals. They bisect each other. So if I were to draw diagonals in here like Miss Edwards was talking about today, if we draw one diagonal, if you draw two, eventually they will cross each other, intersect, and that's something we didn't want to have happen today, but when you have diagonals cross, they will cut each other in perfect halves. And that was 6.7. Those are the theorems we did last week. We did them multiple days in a row. We even did that little activity where we made that little piece of paper thing, and we wrote all the theorem numbers on it so you can remember them. The reason why is because they apply to everything in the next couple sections. Well, the goal today was to intro another property. Something so unique, it needed its own property name. Its own number for a rectangle. So we're going on to the new one, because I think we finished last week with what, 6.8, the theorem 6.8? We're doing 6.14? We're jumping, jump a couple sections here to go to rectangles, so that's what I want to cover. So we're jumping into the first theorem today about rectangles. So here it is. It's 6.13, correction, 6.13 and 14. All right, here's what it says. If your parallelogram is a rectangle, then the diagonals are equal. They're congruent. I'll let you write that down. I'll give you the picture here in a minute.
Does this one have a name?
Yes. It does have a name, and I'll put it up there. So if you want to leave a little space next to theorem 6.13, that'd be a good idea, because it does have a name. And the next one has a name. So, if a parallelogram is a rectangle, then the diagonals are equal. On all the other theorems we did last week about diagonals, I think we had, 6.7, 6.8. We never said the diagonals were the same length. On a rectangle, they have to be. They have to be the exact same length. So here's my picture. There's my rectangle, they have the right angles in the corners, and I have the diagonals drawn, J to L, K to M. Those sticks are the same length. Okay, so if I were to pull out a ruler here and actually measure them, they should be the same number. So this diagonal right here is about 60 centimeters, it's about 59. And I go to the next one, 60, 59-ish, in that ballpark. So they're the exact same length. Now, trying to show why, that takes some of the properties we did previously. Okay, so if you're looking at it, I do have two separate triangles here, and that's kind of what we're looking at. Okay, so here's a triangle, then I have a triangle that overlaps it, this one. In fact, I'll use a different color. So I have a triangle that overlaps, which is this one. If I can prove that these two triangles that are overlapping are actually the same triangle, then the diagonals have to be the same length. Well, duh. Number one, do you agree that both triangles have right angles in them?
Yeah.
Okay, so that's the angle marker. The opposite walls are equal, so they at least have a wall and an angle, and then they both share the bottom wall, which is technically the reflexive wall. That's the one wall that they both share. They both share the bottom. Well, each triangle has three markers now. They have a side, an angle, and a side marker, SAS. So that actually proves that the two triangles are equal, that overlap each other. And if the triangles overlap, then everything about them is the same, including the third angle in the picture. You know, the other angles, the angles up in the corners or the bottom angles, and including the walls. So that wall that went right through the middle, that overlap, that actually intersected, those walls are actually of equal length because of corresponding parts, CP, CP, But again, diagonals have to be of equal length. And that only applies to rectangles, not random parallelograms. They apply to rectangles. So somebody make up a random number.
12.
6, 12, I don't care, let's call it 612. 612 millimeters. So that's how long that diagonal is, J to L. This one has to be the same length, this has to be 612 millimeters. That's a unique property about a rectangle. Now there's other properties we will eventually learn down the road, but for right now this is our one that I wanted to talk about today.
What's the name of that one?
Okay, let's get to the name. Good question. What in the proof I already did. It's called the diagonals of a rectangle theorem. Miss Edwards, if you'd like, fire away. Let's talk about your problem that you want to have.
Alright, guys, I have one problem too for you, it's to take out the door. It can be on that piece of paper again, if you wanna go on the back. You're gonna go to the way back of your book, but I guess most of you are on the computer. So the page number is R6.
R6.
You said an R6 at the very bottom. Wait.
One ticket, once you have it checked, and I saw from Mr. Ward, you're good for the day.
Number 13
Number 13
on
on
R6.
R6. What do you know about these two angles up here? The one that has to be like, these two angles here in the corner. This is corner, this is the rectangle. That's what we start.
So again, this one has to apply to a rectangle. You think about the properties we talked about with rectangles. how we can use the stuff they're giving us.
Number 11. Which one? What number are we doing?
Number 13.
What are these two? The corner number? 90.
Okay, we have it up this corner right here, is right? It's a rectangle, what is it?
Yeah, if you're confused, if you need help, if you have questions.
Right,
Right.
right, because those two angles are adding up to the whole corner, so yeah, that's a good start. This angle is page 60, this angle is. But you're just adding up, you're just adding up.
That's what you were asking.
Those two, but they're add up Well, that's all they're doing right now, is just that's all, that's all.
We'll continue tomorrow. Hey, we'll continue tomorrow. Then.
Yeah.
Continue tomorrow. Hey, bring the little slip of paper back, please. Bring it back tomorrow. We'll continue on with this problem tomorrow.
Now you'll be able to do the